Alright, so today what we are going to do is look in a bit more detail at the problem of scheduling and look at one possible way by which we can pose that problem in such a way that it can theoretically at least be solved in an optimal fashion, but what we will see is that remains a theoretical construct, right? I mean, in practice it turns out that that formulation doesn't really help us to solve the problem, and what we usually need to do is look for other kinds of simpler but faster approaches which give us reasonably good results, maybe not completely optimal. Okay. So first let us look at the problem of scheduling and try to sort of pose it as a well defined problem statement, right? So what we are going to do is assume that you have n tasks numbered from 1 to capital N, okay, and the assumption over here that I am going to make is that this nth task is a sort of a sink, a special case, right? What I mean by that is, it's essentially, if supposing I have a task graph that looks something like this, there are 4 tasks A, B, C and D, right, or I could alternatively also call them 1, 2, 3 and 4, right. In this case I essentially have 2 tasks that I could consider the last task in the graph, right. In other words, if I ask the question which is the last task to be scheduled, I don't have a clear cut answer, right. I could either do B last or D last, both of them will not violate any constraints that I have, right. So to avoid this kind of situation, I am going to introduce one dummy task into the mix, and its goal is just to sort of explicitly say that I now have a concept of a last task. Why is this useful? Because in this way I can say that as soon as this task is scheduled, the entire schedule that I want is completed. Okay. In other words, all dependencies have been met. Okay. Further, I am going to assume that what I am looking for is a so called block schedule, right. To be more explicit, a non-overlapping schedule, right. So unlike the examples that we had last time around, where I saw that I required the ability to basically start the second execution of A before the first execution of ABC have completed, right, in order to meet my iteration period bound. Over here I am going to assume that I can't do that, I have to go with a block schedule. What that probably means in practice is that I may not be able to reach the iteration period bound in some cases, that is okay. I still should be able to get to a block schedule, that is all that I have as a requirement over here. Okay. So what we are interested in is, I have these n tasks, there are now dependencies, right. So the task dependencies are captured by edges. So in terms of terminology, so far we have been using the word data flow graph to represent what we are drawing over here, but in general it is called a task graph, right. Data flow is a more specific case that is used in the context of primarily in the context of signal processing, to indicate that we have a very specific manner of operation. We basically produce certain data which is then consumed by the next unit and so on. But if I was thinking of this as a more general problem, right, let us say in the context of operations research, where I just have a set of tasks that need to be completed in order to finish an overall problem statement, right, or I have a project and in order to finish that project I need to complete certain tasks, right. So then there is no real concept of data flow over here. So to avoid that, what I am just going to use is talk about tasks, task graphs and dependencies between tasks. Okay. As long as I am talking about a blocking schedule, there is no concept of sort of iterative execution that I need to worry about. I could even think about it as though, I just need to complete this once, right. The entire set of tasks need to be completed once. In the operations research context, it would be how quickly can I finish the project. In the context of signal processing, it is how quickly can I finish one iteration of this task graph, right. The fact that I can then repeat it as many times as I want is irrelevant for what we are going to do over here. Okay. So clearly by now you should keep in mind that what I am looking at is a special case of the scheduling problem. Why am I looking at that? Because it turns out that even this special case is computationally intractable, meaning that there are no known fast and good solutions, fast and optimal solutions. Okay? So even if the simplified case is computationally intractable, that should pretty much make it clear that in general, in what we are going to end up doing is we are not going to be trying to look for optimal solutions. What we will do is look for something which is good enough. Okay? So the task dependencies are captured by edges. In general, what we have is if there is an edge from A to B, this indicates a dependency. B can only start after A has completed. Okay? So these are the direct dependencies that we have between the different nodes in the graph. Okay? Now what we have also is a set of resources, and what we can say is that in general there are different types of resources, and we could in particular also consider a case where the situation that AK for k running from 1 to r equals the number of resources of type k. Okay? So this is a situation, for example, where adders and multipliers are treated as different types of resources. So there capital R would be equal to 2, A1 might represent the number of adders, A2 would represent the number of multipliers. Okay? And I might or might not put bounds on the AK values, right? That would essentially correspond to constrained or unconstrained forms of scheduling. I also have a function D. So I am going to use the notation V I in 1 to n to indicate the tasks, okay, which means that I can then say the type of node Vi is equal to some value, right, or rather it is basically the type of resource used for task Vi, and this must obviously be a number in the range 1 to capital R. Okay, it must be one of the resources, right? And I can further talk about the delay of executing Vi given the type of Vi of this is basically the delay of task Vi if executed on resource type T of Vi. Okay? So one way of thinking about this is, for example, if my resources are adder and multiplier, the delay of an addition on an adder might be equal to 1. What would I say is the delay of an addition on a multiplier? I can't do an addition on a multiplier. Okay? So one way of modeling this would simply be to say infinity. So addition cannot be performed on that hardware resource, right? So this is sort of just a general way of capturing our requirements, right? All that I am saying is I have R different types of resources, right? If I cannot execute a particular function on a particular type of resource, I just say that the delay of that function on that resource is infinite. That's as good as saying I cannot execute it, because when I try doing any scheduling algorithm, I will basically find that that straight away kills any latency constraint that I am trying to satisfy. Okay? In practice, of course, we can simplify this, we do not need to do it in this way, right? But this is a general way of sort of posing the problem, at least to start with. Right? A simple variant of this, right, is R is equal to 1, right? This essentially corresponds to homogeneous processors, right? So what do I mean by R is equal to 1? It basically means that I have only one type of processor, Okay, I can think of it as an ALU unit that is capable of executing all the operations that I need to run for my task graph, right? Or I could think of that processor as an actual processor in, let's say, the CPU in my laptop, okay? And each of the tasks is a function that is written in some language like C and then compiled into machine code that will run on that processor, okay? So there is only one type of processor, in other words, I don't need to worry about multiple types of processors. This is obviously a simplification, right? Another even greater simplification is to assume that delay is equal to 1, right? This is the so-called unit delay assumption, right? So what does that mean? It basically says that any task, once it is scheduled on a given processor, will take only a single unit of time to complete, okay? Why are we making all of these simplifying assumptions? Because it turns out that even under these simplifying assumptions, the scheduling problem is NP hard, it is intractable, okay? But at least it allows us to visualize how we can pose this in a way that makes it sort of easier for us to understand how to, how we might be able to solve the problem systematically, okay? So for what is going to follow, I am basically going to make this assumption that we have only a single processor type and that we are working with the unit delay model. I will also mention briefly how we can relax those assumptions when we are sort of posing the problem itself. So what do we have? Let us recap quickly. We have a set of tasks, we have a task graph, and the task graph essentially captures task dependencies, right? There are a certain set of resources. The number of resources is, number of types of resources is given to you. The number of actual resources of each type may be given to you as a constraint for your problem, okay? And once you are given a particular resource, the delay of executing a given task on that resource is also known ahead of time. That is not an unknown, that is actually given to you, okay? Keep in mind that this D could be a variable, meaning that if I execute addition on a general purpose CPU versus if I execute addition on a custom full adder module versus if I execute addition on a serial addition module, right, they could take different delays, okay? So in general, even D depends both on the task as well as the type of resource onto which it has been scheduled. What is our goal? What is the problem of scheduling? The goal of the scheduling problem is essentially to say, come up with a function that takes the task and maps it onto a number in the range 1 to some lambda, where this lambda is some constant, and also along with this we would have, so this is the scheduling problem. The scheduling problem, in other words, is simply talking about at what time instant should a particular task get executed. Further to that, you remember the two other terms that I had mentioned, it was the allocation and the binding, okay? The binding problem would essentially say which resource instance is Vi mapped to, and the allocation problem is how many AK are required, how many resources of type K, right, are required. So the overall problem when we talk about scheduling is sort of, the most general version requires us to solve all three of these. First we have to find out how many resources of each type are required, decide which operation gets mapped onto which particular resource instance, and give the specific time instant at which the operation is going to be scheduled. This constant lambda that I talked about is some number which is essentially used just as a bound. I could have left that bound out and said I just need to map it onto an integer, okay? The reason I am putting some lambda, some constraint over there is, some maximum value over there is so that eventually, because when I want to solve this in practice, I will have to limit the range of values through which I want to search.